Optical transmitters and receivers, design and performance. Optical transmitters and receivers are devices that are essential in the field of optical communication. They are used to convert electrical signals into optical signals that can be transmitted over an optical fiber and vice versa. The design and performance of these devices play a crucial role in determining the speed, efficiency, and reliability of optical communication systems. In this article, we will discuss the principles, design, and performance of optical transmitters and receivers. Optical transmitters. An optical transmitter is a device that converts an electrical signal into an optical signal that can be transmitted over an optical fiber. The basic principle behind the operation of an optical transmitter is the modulation of the intensity or phase of a light source to encode the information contained in the electrical signal. There are several types of light sources used in optical transmit. RS, including light-emitting diodes, LEDs, and laser diodes. LEDs are commonly used as low-cost light sources in optical communication systems. They emit light in a broad range of wavelengths, which limits their spectral efficiency. However, they are simple to operate, require low driving voltages, and can be used for short-distance communication. Laser diodes are more commonly used in optical transmitters due to their high spectral efficiency, narrow line width, and high output power capability. They operate based on the principle of stimulate de-emission of photons, where an electrical current is passed through a p-n junction, causing the emission of photons. The wavelength of the emitted light depends on the band gap of the semiconductor M. Material used. Laser diodes provide high-speed modulation, low driving voltages, and high output powers, making them suitable for long-distance communication. The performance of optical transmitters is determined by several factors, including modulation speed, extinction ratio, and output power. Modulation speed refers to the ability of the device to switch the light source on and off at high speeds, which is critical for high-speed optical communication. Extinction ratio refers to the ratio of the power level when the device is in the on state to the off state, which affects the quality of the transmitted signal. Output power refers to the amount of power that the device can emit, which determines the maximum distance that the signal can be transmitted. Optical receivers. An optical receiver is a device that converts an optical signal into an electrical signal. The basic principle behind the operation of an optical receiver is the detection of the optical signal using a photodetector, which converts the photons into electrons. The electrical signal is then amplified and processed to recover the information encoded in the optical signal. There are several types of photodetectors used in optical receivers, including avalanche photodiodes, APs, and pin photodiodes. APs are used in high-speed, long-distance communication systems since they provide higher levels of sensitivity compared to pin photodiodes. They operate based on the principle of avalanche multiplication, where the photogenerated carriers are multiplied by impact ionization, producing a current proportional to the incident light power. Pin photodiodes are commonly used in short-distance and low-speed applications, where they provide low levels of sensitivity but high responsivity and linearity. The performance of optical receivers is determined by several factors, including sensitivity, noise figure, and bandwidth. Sensitivity refers to the minimum power level of the received signal that can be detected by the device. Noise figure refers to the amount of additional noise introduced by the device into the received signal, which affects the signal-to-noise ratio and the quality of the covered signal. Bandwidth refers to the maximum frequency of the signal that can be detected by the device, which determines the maximum data rate that can be achieved. Design considerations. The design of optical transmitters and receivers is a complex process that involves several factors, including optical and electrical design, packaging, and testing. The following are some of the Optical design considerations for these devices. Optical design. The optical design of the device includes the selection of the light source, coupling optics, and the waveguide or fiber that carries the optical signal. The selection of the light source depends on the application requirements, such as spectral efficiency, modulation speed, and output power. The coupling optics are used to direct the light from the light source into the waveguide. Or fiber, minimizing the losses and reflections at the coupling interface. The waveguide or fiber should be carefully designed to minimize the losses due to scattering and absorption. Electrical design. The electrical design of the device includes the selection of the photodetector, amplifier, and digital signal processing components. The selection of the photodetector depends on the application requirements, such as sensitivity, bandwidth, and noise figure. The amplifier is used to amplify the electrical signal generated by the photodetector, ensuring that the signal is sufficiently large for further processing. The digital signal processing components are used to recover the information encoded in the electrical signal, such as equalization, clock recovery, and forward error correction. The package should be designed to minimize the losses due to reflection and absorption, and to ensure that the coupling between the optical and electrical components is efficient and stable. Testing. The testing of the device is critical to ensure that the device meets the performance specifications and to identify any defects or issues in the design. The testing process includes several steps, such as optical power measurement, modulation speed measurement, sensitivity measurement, and noise figure measurement. The testing should be performed under controlled conditions, such as temperature and humidity, to ensure the accuracy and repeatability of the results. Furthermore, advancements in optical communication technology continue to drive the design and performance of these devices. This has enabled higher data rates and longer transmission distances. Compared to traditional direct detection systems. The use of advanced materials, such as silicon photonics, has also enabled the development of integrated photonic devices with high performance and low cost. Moreover, optical transmitters and receivers have applications beyond traditional telecommunication systems. They are used in various fields ranging from medical diagnostics to military communication systems. In medical diagnostics, optical fibers are used to perform endoscopies to diagnose and treat medical conditions. In military communication systems, optical fibers are used to transmit high speed and secure data over longer distances. In recent years, the demand for optical communication systems has grown significantly. Consumer and business applications such as video streaming, cloud computing, and e-commerce rely heavily on high speed data transmission over longer distances. Additionally, the growing demand for data centers and cloud computing infrastructure has driven the need for high bandwidth, low latency, and reliable optical communication systems. From healthcare to national defense, optical communication technology plays a vital role in today's society. As the technology advances, optical transmitters and receivers will continue to be crucial. Components in various fields and applications. In the healthcare industry, optical fibers are used to perform a wide range of medical procedures. One application of optical fibers is endoscopy, which involves using a flexible optical fiber to mine and treat the inside of the human body. Endoscopes can be used to diagnose and treat conditions such as ulcers, tumors, and bleeding in the digestive tract. Optical fibers are also used in laser surgery, where a high-power laser beam is delivered through a fiber to treat tissues. Optical communication technology is also essential in military communication systems. Fiber optic cables are used to transmit high-speed and secure data over longer distances, allowing military personnel to communicate and exchange critical information in real time. The technology is also used in the development of sensors and surveillance systems that can detect and track military threats. In the field of transportation, optical communication technology is crucial in the development of self-driving cars. The technology allows for the transmission of real-time data between sensors and car's control system. This data can be used to help the car make critical decisions in real time, such as detecting and avoiding obstacles on the road. The growth of the Internet and cloud computing infrastructure has also driven the demand for high-speed data transmission. Optical transmitters and receivers are critical components in data centers.